Hello students, this is Dr. Anita Raj, your chemistry mentor, welcoming you for another session in alcohols, phenols and ethers. Okay, so today we are going to see the general methods of preparation of ethers, right? First, let us see the very important preparation of ether, that is Williamson's ether synthesis. Okay, so actually in this method, an alkyl halide is treated with a suitable sodium or potassium alkoxide. Okay, so in this method, methyl bromide is taken as the alkyl halide and sodium methoxide is also taken. Okay, and now let's see what's happening. Here the sodium bromide is removed. Okay, sodium bromide is removed and we get the ether. Okay, CH3 O CH3, right, plus NaBr, right. So the sodium and this bromine is removed, right. Actually, this reaction involves the nucleophilic substitution of the halogen atom of the alkyl halide by the alkoxide group and may be used for the preparation of both simple as well as mixed ethers. So this is a simple ether. See, both alkyl groups are same, okay? And also it's possible to prepare the mixed ether. See, here I have taken sodium phenoxide. So this is a benzene ring, okay, phenyl group. So sodium phenoxide, and when it is treated with alkyl halide, we get the mixed ether. Same type of reaction takes place, substitution, okay? So here this gets removed, okay? And finally we get the product OCH3. Okay, so this is methyl phenyl ether. Okay, this is methyl phenyl ether. Okay, this is dimethyl ether and this is methyl phenyl ether. Understood? So actually, this Williamson synthesis involves SN2 attack of an alkoxide ion on primary alkyl halide. Okay, so this is the alkoxide ion. Okay, and this attacks the alkyl halide by SN2 mechanism, right? And let us see what's happening here. See, actually, in SN2 mechanism, the attacking nucleophile will be attacking the substrate molecule from the rear side. Okay. See, this is what happening. See, actually, this attacks the uh, reacting molecule. Okay, on the rear side. Okay, and the already present nucleophile. So this is the nucleophile which is already present. This nucleophile will be leaving the molecule from the front side. Okay, it will be leaving the molecule from the front side. Therefore, this SN2 reaction is always followed by an inversion in configuration. So this is what happening actually. So let me write the product now. Then we'll get the product NaBr. See the product now. See, the attacking nucleophile is attacking the reacting molecule from the rear side, and the nucleophile which is present already will be leaving the molecule through the front side. So here this attacks this side, okay, and finally there is an inversion of the product, okay. The inversion in configuration is taking place, which is called as the Walden inversion. So the Walden inversion we can see only in SN2 mechanism. See, just opposite side we are getting, okay, just like an inverted umbrella. Understood? So this is called as Walden inversion. Actually, in Williamson synthesis, we are having certain limitations. See, this Williamson synthesis is not applicable when the alkyl halide used in the synthesis is tertiary, since it produces an alkene instead of an ether. See here, when you are making use of a tertiary alkyl halide, it will be giving the alkene as a major product. Okay, so instead of ether, right? So that's a major limitation. So let us see what's happening here. So the reason is that the tertiary alkyl halides are highly susceptible to dehydrohalogenation in the presence of sodium alkoxides, okay, which is a strong base. Okay, let me give an example for that. So I have taken tertiary butyl bromide. When this is treated with an alkoxide, sodium alkoxide, okay, when this is treated with sodium alkoxide, see, let us see what's the product formed. Actually, what's happening here is we'll get this. See, this is, Br will be reacting with sodium, and we'll get sodium bromide. Okay, that's one of the product. And then what happens is this RO, okay, this RO, and one hydrogen from this methyl group will be removed as ROH. will be removed as ROH, alcohol. So what will be remaining? We'll have CH3, C, CH3, double bond, CH2. So it is an alkene. Okay, it is a double bonded compound. We will get alkene. So this is what happening. Can you understand? So see the product CH3, C, CH3. Then here we will have CH2 because one hydrogen has combined with RO to form alcohol. Okay. So these are the products when an alkyl halide, tertiary alkyl halide is treated with sodium alkoxide. Okay. So if you want to change this, so instead of using this tertiary alkyl halide, we should make use of sodium tertiary butoxide. Can you understand? So that it's not possible to produce the alkene, and rather we'll be getting the ether. Okay, instead of using like this, we should make use of like this. Okay, so here let me explain how the process goes on. We have taken sodium tertiary butoxide. Okay, sodium tertiary butoxide. When it is treated with ethyl bromide, here what's the product form? This sodium bromide is removed. Okay, sodium bromide is removed, and we'll get the ether CH3, C, CH3, CH3, O, then you write the rest C2H5. Okay, so C2H5. So this is a mixed ether. What's the name of this compound? Ethyl tertiary butyl ether. Ethyl tertiary butyl ether. Okay. Next method is by dehydration of alcohols. See, when the excess alcohol is heated with concentrated sulfuric acid at 413 Kelvin, the alcohol undergoes dehydration to give a symmetrical or a simple ether. Okay. So when excess alcohol, I have taken ethyl alcohol, when it is heated in the presence of concentrated sulfuric acid in the at temperature 413 Kelvin, water molecule will be removed. That is, a dehydration takes place. Okay. So H2O is removed. And finally we'll get CH3, CH2O, CH2, CH3. See, this is a simple ether. On both the sides we have the same alkyl group. Is it up? So it's called as a simple ether or a symmetrical ether. Okay. So diethyl ether is the product. Diethyl ether. See, we are also having certain limitations under dehydration of alcohols. The first one is the temperature should be properly controlled, or else alcohols will produce alkenes as major product. Okay, can you understand? So the temperature should be maintained as such. If the temperature is raised automatically, instead of producing ether as the major product, we'll be getting alkenes. Can you understand? The next important limitation is this method is suitable only for primary alcohols. See, this is the ethyl alcohol is a primary alcohol. Okay, and not with secondary or tertiary alcohols. So it's not possible to produce ethers very easily from secondary or tertiary alcohols. Okay, so dehydration of alcohols is a suitable method for producing ethers from primary alcohols. See, here I've taken isopropyl alcohol, which is a secondary alcohol. See, this carbon OH group is attached to the secondary carbon, so it is called as a secondary alcohol, that is isopropyl alcohol. When this isopropyl alcohol is heated in the presence of sulfuric acid at 413 Kelvin, we'll get the alkene. Okay. So let me write the product now. What's the product? CH3, CH, double bond, CH2. Okay. So this is propane, and this propane will be the major product. Okay. So it's an alkene. Along with this, we'll be getting a minor product, that is ether as a minor product. So CH3, CH, here CH3, O, CH, CH3, okay, CH3. So this is a diisopropyl ether, okay, diisopropyl ether. This is a isopropyl group. This is also on another isopropyl group. So diisopropyl ether, okay, and this will be a minor product, but whereas this alkene will be a major product. So only primary alcohol is used to produce a proper ether by dehydration of alcohol method. Okay. Okay. The next is by the action of diazomethane on alcohols. Okay, action of diazomethane on alcohols. So actually methyl ethers can be prepared by treating an alcohol with diazomethane in the presence of fluoroboric acid, HbF4 as catalyst. Okay, see this is diazomethane CH2N2. Okay, CH2N2 diazomethane, and when it is treated with alcohol, ethyl alcohol in the presence of HbF4 as catalyst, what's happening here? This hydrogen gets attached to the CH2 and this nitrogen is removed as nitrogen. Okay, N2 is removed. Okay, this N2 is removed as nitrogen, and what happens here? We'll get the product CH through CH3, CH2, okay, then O, then CH3. Can you understand? So this is ethyl, methyl ether. Okay, ethyl methyl ether. See here, let me explain once again. This hydrogen combines with CH2. So we are getting CH3 here. And this CH2 CH2O gets attached to CH3 directly. So we are getting ethyl methyl ether. Ethyl methyl ether. So next is from the lower halogenated ethers, and higher ethers can be prepared by treating lower halogenated ethers with suitable Grignard reagent. See here, this is Grignard reagent. Okay, see the RMGBr. So we all know RMGBr. This is the general format for the Grignard reagent, is it not? So instead of R, I have written C2H5. So the same thing, Grignard reagent. So what's happening here is this is methoxy. This is methoxychloromethane. Okay, methoxychloromethane. Right. So in here, what happens here? This Cl gets attached to this one. Okay, this Cl is removed. Okay, and finally we'll get the product CH3O. Okay, CH2, C2H5 plus NgClBr. Okay, so what is this? This is methoxypropane. This is methoxypropane. Okay, this is methoxypropane. Okay, so methoxypropane is the major product. Okay, so we are getting the higher ethers from lower ethers. Understood? Well, fine students, I hope you might have understood what I have taught today. Let me meet you with another important topic in my next session. Until then, it's Dr. Anitha, your chemistry mentor, signing off from you. Thanks for watching.